Hello, I'm discussing single-wall nanotubes. Single-wall nanotubes are sheets of graphene that have been rolled up to form a long hollow tube with wall thickness of single atom. Single-wall nanotube is generally has diameter of 1 to 2 nanometer and a length up to 100 micrometer. Their one-dimensional structure gives them extraordinary mechanical, electrical, and thermal properties. These properties have been exploited for application in flexible electronics, sensors, and energy storage. Structure of single-wall nanotube and multi-layered nanotube. Single-wall nanotube versus graphene. A cylindrical tube formed by rolling a single layer of graphene into seamless tube. A two-dimensional sheet of graphene atoms arranged in a hexagonal honeycomb lattice. Diameter typically 0.4 to 2 nanometer. Graphene thickness 1 atom thick. Electronic properties depend on the chirality and diameter. Graphene exhibit high electron mobility and conductivity, can be metallic or semiconducting, intrinsically metallic but with a zero band gap, can be modified to semiconducting under certain conditions, high thermal conductivity along the tube axis. Among the highest thermal conductors known with excellent heat dissipation in two-dimensional extremely high tensile strength and flexibility, exceptional mechanical strength with one of the highest known Young's moduli, nanoelectronics, energy storage, sensors, composite materials, drug delivery, electronics, transistors, coatings, energy device, composites, and transparent conductive films. Properties of single-wall nanotube. The single-wall carbon nanotubes properties that have attracted so much interest in recent years are their unique physical properties and structure, electronic, optical, thermal, and mechanical properties. The single layer of carbon atoms is held together in the tube structure by hybridized sp2 chemical bonds. Depending on the chiral angle of how tube is formed and depending on the chiral angle of how tube is formed and they are considered semiconducting or metallic nature. Single-wall carbon nanotubes are inert and can be used to increase mechanical and conductive properties in other materials. Physical properties of single-wall nanotube. The unique physical properties of single-wall nanotube come from their one-dimensional size, shape, their aspect ratio, and sp2 hybridized carbon atoms arranged in a hollow tube-like structure. They consist of a single tube of carbon atoms arranged in a hexagonal pattern having 5 to 6 members rings. There are different types of single-wall nanotubes because the graphitic seeds can be grown with different chiral angles during synthesis. True single-wall carbon nanotube are 0.7 to 1.2 nanometer outer diameter and can be anywhere from 0.5 to 30 micrometer long, and longer ones are available up to 500 micrometer. Structure of single-wall nanotubes: armchair or single-wall carbon nanotubes with equal N and M indices and chiral angle 30 and shows electrical properties similar to metal. Zigzag. In this structure, the tube axis is perpendicular to carbon-carbon bonds. A single-wall carbon nanotubes with N-M indices equal to N0 and OM and chiral angle 0 degree and can be either metallic or semiconducting. Chiral NM nanotube is chiral if it has type NM with M greater than O and M not N, then it's enantiomer. Enantiomer mirror image has the type Mn, which is different from Nm and chirality structure and essential for future high-end application replacing silicon in next generation electronics. Electronic properties of single-wall carbon nanotube. Single-wall carbon nanotubes electronic properties are determined by the chiral structure, diameter, and length. Having the diameter in the nanometer range gives them quantum effects. They can either conducting or semiconducting on their chirality. Geometry determines the bone structure and energy. And energy band gaps. Single-wall carbon nanotubes are an important type of carbon nanotubes because their properties change significantly with differing NM values. The band gap can vary from 0 to about 2 electron volt and can show metallic or semiconducting behavior. Optical properties of single-wall carbon nanotubes. Single-wall carbon nanotubes can be used for their light absorption, fluorescence, and transparent conductive properties. They have known to successfully make super blank light-absorbing materials when using a carbon nanotube or a individual carbon nanotube standing up like a forest because light gets trapped between the individual carbon nanotubes and cannot reflect back to the observing properties and their length. Single-wall carbon nanotubes have been used at very low loading 0.03 percentage in weight to make transparent conductive films for displays and solar cells to replace indium tin oxide, which has limited global resource. Thermal properties. Carbon nanotubes are known to be efficient thermal conductors. They conduct heat along the tube axis, exhibiting ballistic conductivity. They are considered insulators for heat moving laterally along the nanotubes axis. Or individual single-wall carbon nanotubes has a room temperature thermal conductivity of about 3500 watt per mole per Kelvin along its axis, which is many times higher than copper 385. Structural defects strongly affects the single-wall carbon nanotube thermal properties, such as defect leads to photon scattering, reducing the thermal conductivity of nanotube structures. Mechanical properties: single-wall carbon nanotubes are one of the strongest and stiffest material discovered. They are physically strong and mechanically flexible, making them fantastic fiber additives. Their legendary strength is due to covalent sp2 bonds formed between individual carbon atoms in their structure. Some research has shown they have average breaking strength from 13 to 52 gigapascal. They are very resilient ability to recover quickly or adapt well to challenge difficulties or change. When they bend, they buckle but do not break. In fact, they can easily be straightened out without any damage to their physical structure. Their theoretical Young's modulus range from 1.28 to 1.8 dpa terapascal, while 0.21 dpa is in steel. Application of single-wall carbon nanotubes. Single-wall carbon nanotubes application include advanced electrodes, energy storage, conductive films, and coating, including transparent conductive coatings. Solar electronics thermal interface materials, structural materials, catalyst supports, biomedical and sensor applications. Single-wall carbon nanotubes have been applied as the most basic building block of these systems. The electric wire having the nanoscale diameters and all nanocarbons structure makes them excellent conductors. Their electrical and thermal conductivity combined with their superior mechanical properties make them ideal candidates for cutting-edge advanced material applications. Okay. Their electrical and thermal conductivity combined with their superior mechanical properties make them ideal candidates for cutting-edge advanced materials applications. Okay, it's all about single wall carbon nanotubes. Thanks for watching and request you all like, comment, share and subscribe. Thank you for patience. That is now bye bye. See you.